Hello, welcome back. Today we are doing notes 8C, which is on electric currents and magnetic fields in electromagnets. You are going to do the top section of the notes by yourself. If you are doing this digitally, the link is in today's folder, which is week 3, Thursday. If you want to type in your answers, I do have paper copies available at school if you would prefer. But you are going to do this section on your own and then just either compare them with friends or ask me to look at it to make sure you have the correct answers. All right, so in 1820, a Danish scientist, and Danish means that he's from the country of Denmark, a Danish scientist named Hans Christian Ørsted. That's pronounced Ørsted. And it is likely that you are going to have his name on the SOL. I don't think you're going to need to know the year, but you might need to know his name, Ørsted, and that he's the one who discovered what he discovered. So what did he discover? He discovered the relationship between electricity and magnetism. When during a class demonstration, so he was a college professor. He taught physics, and electricity was a new thing. It had just been kind of discovered and started to be disseminated, and they were running electricity through a wire to show something, and then they were using compasses for something else. And he noticed that when a compass that had been set down by accident near the wire, when the wire got turned on, that the compass moved and pointed toward the wire. He was like, what's going on with that? So he started to do some more tests. So when he ran electricity through a wire with a compass that was nearby, he noticed that the compass needle moved when the current was flowing. So he performed further tests. He set up compasses around a wire, and when he turned on the electric current, the compass needles lined up in a circle around the wire. Pause that if you need to get caught up, but I'm going to erase it and move on. So down here at the bottom of the notes, I've got a image here that kind of shows his setup. So he would have had a wire, and then it was a wooden board rather than acrylic like in this image. But then he put the compasses around it, and as you can see, it makes a circle with the compass needles. And that basically shows you where that electrical or that magnetic field is that was caused by the electrical charge. All right, so you already know that matter's made up of, that's right, atoms. And atoms are made up of 3 particles: protons, neutrons, and that's right, electrons. We know that protons and electrons have an electrical charge. Protons are positive, neutrons are neutral, and electrons are, that's right, negative. So protons are positive, neutrons are neutral, have no charge, and electrons are so negative. Oh my God, ew. I know, it's dumb, but the dumber it is, the more likely you are to remember it. Protons are positive, neutrons are neutral, and electrons are so negative. Ew. I can't even do the hair flip right. Anyway, and electrons have a negative charge. When electrical charges flow through a wire or a similarly conductive material, they create an electric current. This is measured in a unit called amperes or amps. This is the push that the electricity is provided. The voltage is the actual amount of electricity. The amperage is the push. And they'll say all the time that when you get shocked, it's not the voltage that gets you so much as the amperage. So amperage is basically current. So current equals the voltage divided by resistance. I've got it right there, and anyway. Voltage divided by resistance. Amperes are named for Andre Marie Ampere, who was French, and there were a whole lot of French scientists figuring stuff out at this time period. This unit tells the amount of current flowing past a given point each second. So I is the inducted current, the amperage. V stands for voltage, and R stands for resistance. Now, I don't think that you are going to have to do any current calculations on the SOL, but you might well need to recognize I equals V over R as the way that you figure out the amount of current in a wire. Like you might just have to recognize that formula, not use it, but recognize what it's for. All right, again, pause it if you need to keep going, but I'm going to clear it and move on. All right, an electric current produces a magnetic field. Iron filings scattered around a wire show, like this, we've got an example of that right here, show the lines of the magnetic field produced by a current in a straight wire in the shape of a circle with the wire at the center. So we've got the wire here at the center and then this card here, and you can see where they scattered the iron filings and that they lined up in circles. Ampere carried out many experiments with electricity and magnetism. He hypothesized that magnetism is the result of circulating charges and that objects can become magnets or magnetic because of the motion of electrons. So if you get the electrons moving in the right way, you'll have a magnet. Just to look at the rest of the pictures before we move on, here we took that single line of wire and we wrapped it into a coil, and we can see what happened to those circles of magnetism. It got bunched up inside of it. And then here we have a model of an electromagnet. We've got the wire going around, we have our battery, we have our switch, and then our iron nail that has the coil of wire wrapped around it. Oh, where'd I go? Okay, so again, hopefully you paused it if you needed to, and we will move on. All right, on to the back. Electromagnets, thanks to Ørsted and Ampere. So it was Ørsted's initial discovery and then Ampere's experiments with that information that led us to our current knowledge about electromagnets. So we know that electric current creates a magnetic field and that it can be turned on and off with the flow of electricity. So it's going to be difficult to do this if you're doing these notes digitally, but if you are doing them digitally, there's a way to do this. You can just insert a drawing and then draw in circles using your touchscreen if you have it, or you can just draw them with the mouse. Or just drawing a magnetic field. So if you just like wanted to insert an arrow and do circle arrows around it, that would be fine. So the magnetic field around a current carrying wire forms a cylinder. So do you see how we have that thin wire in the middle, and then once the power's turned on, we have this like column, we have this cylinder of electrical energy that's going down the wire. If the wire is twisted into a loop, the magnetic field gets bunched up inside the loop. So if we have a simple loop here, we've got electricity, these magnetic fields that are all around our loop of wire. If we coil it, just like the image on the other side, we get those big loops. Now you don't have to draw that part. You do need to draw that part though. Again, pause it if you need to, but I'm clearing it and moving on. The strength of the magnetic field increases as the number of loops is increased. So the more loops, loop with 18 million O's. As the number of loops is increased. So the more loops you have, the stronger your electromagnet. By winding a current carrying wire into a coil, you have strengthened the magnetic field at the center of the coil. A current carrying wire with many loops is called a solenoid. And that's just a fancy word for a loop of wire that carries electricity. It's called a solenoid. The solenoid creates a magnetic field that can be turned on and off by turning the electricity on and off. So imagine how difficult it would be to move something very heavy like a car or a big thing of scrap metal if we didn't have electromagnets, if we didn't have some way to put the magnet over top of it, turn the magnet on, raise the thing up, move it over to where we want it, and let it go and turn the magnet back off. How would we get rid of that heavy thing if it was a permanent magnet and we weren't able to turn it off? It would just be stuck there and we'd never be able to get it down. Think about these things. When we have electromagnets, we do have north and south poles, just like on a bar magnet. So you know how the classic bar magnets that you saw when you were in the lower grades that had blue and red and north, N and S for north and south. But what's cool about electricity is that you can reverse which one's north and south by reversing the current. So you can, for example, pick something up and then reverse the current and not just put it down, but push it away. So with the same amount of force that you attracted it, you can then push it away because you've reversed the north and south poles. All right, again, pause it if you need to. I'm clearing it. So how do we make an electromagnet? We wrap a solenoid. And what was a solenoid? That was a fancy name for what? Right, a coil of wire. So solenoid is just a fancy name for a coil of wire. Wrap a solenoid, a coil of wire, with an electric current around a ferromagnetic material. And what do we mean by that? We mean iron or something that's got iron in it, something that's got enough iron in it to make it a magnetic metal. Iron on the periodic table back there is number 26, and that's Fe. Why isn't it IR? Well, because a lot of the elements were named in Latin, and ferrum is Latin for iron. So Fe, iron, ferrum. So that's where ferromagnetic comes from. It's an iron-based metal. So when you wrap the solenoid around our ferromagnetic metal, the existing magnetic field will be increased, and this creates an electromagnet. An electromagnet is a strong magnet that can be turned on and off. Oh, I can stick it here. Okay, so to increase the strength of the electromagnet, there are 4 things to be done. Number 1, give it more juice. So give it a bigger battery. Plug it into the wall. Do more batteries. Something that just gives it more electricity, give it more energy. Add more coils to the wire. So if you only had 3 coils, add a whole bunch more and your thing will get stronger. Wind the coils of the wire closer together. So not only can you add more coils, you can also put them closer together. So a electromagnet that was made with one, two, three, four, five, six, 7 loops that were spread out like that is not going to be as strong as one with those same 7 loops. One, two, three, four, five, six, seven. Aren't I good? With those same 7 loops that are tighter together. This is going to be stronger than this. And then finally, use a stronger ferromagnetic metal for the core. So you could imagine that this electromagnet made from a nail and wires is not going to be nearly as strong as this one that has an iron bar as its centerpiece. And we will use those next week. All right, so make sure you have all that. Get it all typed in, written in. Have a lovely day. Make good decisions. Bye.